Hello everyone, this is a talk on ArcGIS API for Python for analysts and data scientists. I'm Atma Mani, I'm the lead product engineer for the Python API, and joining me today is Andrew Chepkowski. Before we get started, let's do a quick recap on what the Python API is. The API can do multiple things. You can do things like you can use it to automate the management of your GIS. What I mean by that is you can use that to create new users, move them around, assign them licenses, manage your servers. You can also use that to manage and automate creation of content on your GIS, things like publishing layers, publishing web maps, cloning from one organization to another. Then you can also use it to perform spatial analysis. You can do things like drive big data tools, perform spatial analysis, run spatial analysis tools and imagery analysis tools on your data that is stored on your web GIS. So this talk is primarily going to be focused on the last part, which is performing spatial analysis or data science using the Python API. As you know, the Python API is designed to work against your web GIS, but it can also use local datasets. A lot of our talk today is going to be looking at how you can run analysis against your data that is stored on your web GIS, but also read data from your local file system and then analyze and push results back into your GIS. To get started, this is what we're going to look at today. We're going to start with looking at standard spatial analysis or feature analysis. We'll do a little bit of demo. One example of finding suitable locations for siting new bus stops. We'll look at how you can perform geocoding, how you can perform network analysis, how you can do geo-enrichment, how you can analyze imagery or raster data, another suitability example over here. And then how you can integrate with third-party tools. What we mean by that is how you can work with the scientific Python analysis, libraries in the scientific Python ecosystem. And then we'll conclude. So to kick it off, I'm going to hand it off to my colleague, Andrew Chepkowski.
Hey, thanks, Emma. Okay, so now we're going to focus first on feature analysis. And let's go ahead and take a look at that. To do our feature analysis, we're going to use the ArcGIS API for Python. And the ArcGIS API for Python is a collection of modules and widgets that you can use both within the Jupyter notebook environment, which we'll show in a minute, or from your IDE to do analysis. It's complementary and it works well together with both ArcPy and other third-party modules. There's applications to do geo-enrichment, geometry operations, geocoding, network analysis. There's feature analysis, feature operations, the spatial-enabled data frame, and deep learning as well. And we're going to cover some of these as we move forward. But before we go on, I just want to say that ArcGIS API for Python plus Jupyter gives you a very rich and visual experience. It allows you to create these reproducible workflows and to share with your colleagues so they can either check your work or you can share what you're doing throughout your organization very easily. And now, with the latest release of Enterprise, you can even have hosted notebooks that store all this information and a common place to save all your notebooks. So let's go ahead and learn about some of the things. But first, the Python API all starts with your GIS. And we do from arcgis.gis, import GIS. And then we provide our credentials. In this case, we're using a named user called demo del dev. And we're connecting to ArcGIS Online. When I run cell number 2, I was prompted for a password and I typed it in. I can also connect to my enterprise or portal. This is my local instance that I have stored somewhere on a server that I manage completely myself. So I do GIS, provide the URL, and since it's a named user, I provide the username and password. Now I can go ahead and start searching for content. So there's a rich search engine, think of it like Google, and we can go through and find items. Items could be anything from static files to actually services itself. So you do gis.content.search and you put in what you're looking for. And you can limit it by title, like we have here, San Diego. So it's going to find everything that is related to San Diego. Or we can even limit it by type, such as we're looking for feature layers or shape files or file geodatabases or whatever. And and then we can go through, and in Jupyter, we get a rich visualization experience. So we're going to go through and we're going to loop, and we're going to do from item in items, and then display each item out and get this rich visualization within our Jupyter notebook. Once we have the items we want, we can go ahead and place them on a map. Here, I'm going to do gis.map, pass in the location of where I want to go, in this case, San Diego. I'm going to set a zoom level, in this case, 14, and I'm going to add some layers. I pulled in the trolley stations and attractions, and with this, I could go ahead and do some analysis. Maybe I want to know, I want to compare the distance from these attractions to trolley stations to see if I want to, where I need to put a new trolley stop. And that leads us to spatial analysis. And this is how we're going to discover relationships, patterns, and trends within our data. And in the Python API, it exists in the ArcGIS.feature submodule. And this contains a whole host of tools. And we're going to look at a couple of them, and then we're going to see them in action. The first set we're going to look at is it's going to allow us to aggregate data. These are our summarization capabilities, our find locations, data enrichment, and analyze pattern. And those are all our spatial analysis tools. So with summarized data, you do ArcGIS.features, and then it's in the summarize data submodule, and there's functions. So let's look at aggregate points. Here we would pass in our point data set and our aggregations, and then the fields that we want to summarize by. We get back a new layer, and then we can add it to the map. And we can render it based on class size renderer or some other way we want to, or we can accept the default way that people are rendering the data. We can also enrich layers, and this is going to allow us to add demographic information that we might not have from a point or polygon or polyline. In this case, we're going to enrich this layer for police beats, gets our analysis variables. In this case, this is various variables that are associated with education, and we're going to add them on. We're going to do that query and get our heads from display the first 5 records. We can do proximity analysis, and this is going to show us to see what is near what. So we do plan routes. In this case, we have our relief centers, we have our start time stop, and where our stadiums are, and we want the stop service time to be 30 minutes. And we get back our information as layers that we can add back onto our map. We can do the same thing with creating buffers. We pass in the size of our buffer, the output file name, and the location. And we can manage data as well, and this allows us to do those more geographic operations such as dissolve, extract, merge, and overlay. And we see that here by calling overlay layers, passing in our information with intersect, and it saves the data out to a hosted feature service layer. And then we can also interpolate points, find hotspots, find outliers, and calculate density. We can take point data, and let's say we have a category like rainfall, and create that continuous surface for the area where our points are based on some extent. So let's go ahead and take a look at some of this in action. Here I have an example of looking at access to public transit. And the goal here of this data set, this example, is the city of Chattanooga, Tennessee, is putting in a new bus stop route and bus stops, and they haven't decided where the most need is. So we need to create a map that basically finds the best area or the most in need area of where we're going to do this, or where we're going to put this new stop. So it starts by setting up our environment, and this is where we're going to do our imports. So we're going to import some standard library things such as OS, but we're also going to go ahead and import pandas as PD to shorten it, ArcPy, and then ArcGIS API for Python. We're going to pull in the analysis, enrich, as well as feature layers, and then our GIS object. I'm going to go ahead and connect to ArcGIS Online by doing GIS equals GIS, and I'm going to use a profile in this case. This is a protected way where I can store named users and passwords. My data comes from the general transit feed information model for the stops, and I'm going to pull that information in. I downloaded it previously, and I can go ahead and pull that information in. And let's take a look at it. So I'm going to use pd.readcsv and look at the stops. Here we notice we have a geographic location of stop lat and stop long, plus some other information on here, such as the stop ID, stop count, the name of the stop, etc. We can go ahead and we can convert this using ArcPy, because there's a built-in tool to do this for our stops, by doing arcpy.conversion.gtfs stops to feature, and this is going to create a new feature class. I'm then going to take that information and import it to its spatial-enabled data frame. So using pd.dataframe.spatial, I'm going to do dot from feature class and put the path of that stop feature class in there. And I'm going to show the top 5 records. We can go ahead and, using the power of the spatial-enabled data frame, visualize that information on the map. I'm going to take my stop spatial-enabled data frame, do .spatial.plot, and then following the syntax that's very similar to matplotlib, I'm going to put the information on a map. I'm going to specify the marker size, the color step, the color map, and the line width for the outline of my points. This is going to create a map view object. I'm then going to go ahead and modify the base name and display it for users to be able to see. Having this information, I'm going to leverage the analysis component of the ArcGIS API for Python to do drive time analysis. So I'm going to call create drive time areas off the analysis endpoint and pass in the first and second 500 stops for the city of Chattanooga. I have to do that because for this tool specifically, there's a limitation of 500 points that you can pass in. I'm going to set the break value to 5 for each one because I'm interested in people walking towards the facility. I want it to be walk time in minutes, and I want to dissolve all overlaps because I want to know the areas that are well served. I'm going to set future to true, which is going to return back a result object, a future object that's going to allow me to continue doing my analysis. So I can fire off both of these analyses at the same time. Now that I have that, I'm going to merge my data together and save it, and then dissolve the geometries together and create a new feature class using arcpy.dissolve management. Now that we've merged our two geometries together, let's go ahead and start figuring out what areas are the most underserved based on our stop data. To do that, I'm going to gather some census block boundaries and enrich them. We can see that we don't have any census data here, and visually we can see that it does overlap our points after we did a simple query. Now we can use that enrich function of the analysis, pass in our blocks, and specify the following variables, which is the 2019 population counts, the area, available car data, and the number of families below the poverty line, basically poverty data for each of our blocks. And we can go ahead and we can see how it enriched our data set and added this information in based on the appropriations. We're then going to go ahead and calculate the bus stop coverage. Now that we have that, we're going to go and read our feature class for our saved drive times, and we're going to set some values. We're going to calculate some population density based on square miles. We're going to figure out the number of points that exist in each block, and then we're going to create stops per person calculation based on the stop count that we calculated in the step before and the population density. Once we have that, we can then determine well-served areas. So we're going to save our spatial data frame back to a feature class, and then use the arcpy.analysis.erase to erase out areas that are already well covered based on our walk times. And this will give us our final spatially enabled data frame block. We can then go ahead and pull out using intersection the indexes where it intersects our stops spatially enabled data frame, and then save, and then make an additional subset on our SDF blocks final. We can go ahead and visualize this on a map. And what we end up having here is this query. This query is basically our criteria that we've set up. We're saying if the stops person is less than 5, stops per person is less than 5, and we have high levels rates of poverty and low levels of car ownership, and the block density is over a certain number, then we want to consider those for areas where we need to add new bus stops, because we have the high population and a lot of people who can't get from point A to point B because they don't have the ability. They either don't own cars or they don't have the ability to own cars. And we can plot this on a map, and then we can take our final map and save it out to our enterprise and share it with the policymakers so they can make a better informed decision on where they have to put their next set of bus stops and routes. So we're going to switch back and move on, and we're going to talk a little about geocoding. And what geocoding is going to allow us to do is going to allow us to find a location on Earth from some piece of descriptive information, such as an address. And the geocoding module in ArcGIS.geocoding has the ability to do standardized single-line geocoding, batch geocoding, which is a collection of addresses, and reverse geocoding. And let's take a look at how this works. So we can pass in either a single line or a dictionary of multi-field addresses. And we see that in the lower left and lower right-hand side of the screen. With the single line example, we're going to use the example of 380 New York Street in Redlands, which is Esri's corporate headquarters. And we're going to pass that into the geocode function. This returns back a list of locations. So we're going to grab the first one, add a pop-up, and we're going to draw it on the map. And we can see we get the point of the location that's associated with that XY location. Another interesting thing that we can do is we can also geocode for points of interest. Let's say you're going to be in the city of San Francisco, and you know the extent of the area that you're going to be in. We can pass in to geocode Starbucks and then Union Square extent and the number of locations we want, 100, and we can find all Starbucks and plot that on the map as well. And we can do this for both cultural, geographic landmarks, businesses, or categories, and administrative subdivisions. If you have a list of single line or multi-line addresses, we can pass that in as well to batch geocoding, and it'll geocode them all at once. The result comes back as a list, and that means you just iterate it doing 4 address in results, and then you can either draw or save out those locations and as well. Reverse geocoding is giving a set of lat-long or XY locations and getting back the address at that location. So here we have our point location, and for a reverse geocode, and I'm going to set my language code to French because this area is in France, and we get back the address for that XY location. The next component that I want to talk about is Network Analysts, and this is where you do routing, directions, location allocations, service areas. And the Network Analyst has a whole set of capabilities. We can do simple routing, optimized routing, service areas, location allocation. You can find closest facilities from your existing location. So think of it, if you're a EMT and you need to route going from you're at a crash site, you could auto route and find the closest facilities from where you are. You can solve the vehicle routing problem or the traveling salesman problem. You can also get real-time traffic and origin destination cost matrix. So there's a lot of stuff we can do. It's considered a commercial grade analysis, and it's backed up by multiple data sets. So let's look at service areas. So let's say we have our travel mode and we want to travel by truck. So we can go through and pull in our travel modes that's available for the network analysts, and each one can have its own defined set of travel modes. And we're going to pull that in, and we're going to look for trucking time. We can then take our layer and do solve service area, pass in our locations, set the default breaks, which is in minutes, so 5, 10, and 15 in this case, traveling in the directions from the facility. So we want to know how far our fire trucks can go from their starting point, which is the fire station house, going to whatever incident we have. And with these maps, because this data is very important to know, because we need to know how far a truck can travel, the fire truck can travel to get to its desired incident, because time is critical in these things. So let's go ahead and take a look at a demo of doing network analysts and geocoding together. So I'm going to swap over, and we're going to just do a simple example of network and geocoding analysis. So ArcGIS network analysis is going to allow us to solve these network problems, and some of the examples would be finding routes across the city, identifying closest emergency vehicles, facilities, etc. So to do that, we can go ahead and we can construct drive time based service areas. So I'm going to go ahead and connect to my GIS, and I'm going to bring in from the network analysis my service area layer, and I'm going to pull in my route layer. Each enterprise or online organization is has a registered service area that you can pull in. Change profiles. So we have our service area loaded. Now we're going to go ahead and we're going to geocode an area. So I'm going to geocode the result just for Palm Springs, California, and return the value as a feature set. This is going to allow me to cast it to a spatially enabled data frame for all results. You can see we got 5 rows back for our geocoding result. Let's go ahead and display that on a map. So we create our map, and then we're going to do our spatially enabled data frame .spatial.plot, put the points on the map, and we can see that we have our location show up on the screen in green. Now we're ready to compute our service areas. We saw before on the slides how to get the travel modes for the supported modes. In this case, I want to get the driving time. So I'm going to pull that information in and then change my spatially enabled data frame to a feature collection. Now I can go ahead and I can create my drive time areas. I pass in my feature layer collection, my break values, and I'm going to set the value to true. This will get me back. This will return back a result object that will allow me to continue on and continue doing my job, just like all analysis tools. So I can do my drive time job.status, and I can see that it's still executing. To get the result, I take that result object and do result as a method. We get it back, and it'll wait for the job to finish. In this case, the job is still running, so you can see the execution was paused. Once it's returned, you see I get back a feature collection, and I can go back and we can add it back to the original map. And here's the drive time distance that we can get from the various points that we geocoded. We can go ahead and we can get driving directions from routing. So in this case, I'm going to pull in routing directions from ArcGIS Online. I'm going to create my route layer, and I'm going to do some geocoding. In this case, I'm going to geocode some addresses within Berlin, Germany. So I'm going to use batch geocode this time, pass in my stops, return it back as a feature set, and take a look at the results. We can see from the spatially enabled data frame that we have our X and Y coordinate for each stop, and we can go ahead and we can use that for geocoding. Let's go ahead and pull that information out and get it in the format that we need to do geocoding, and then pass it into the route service.solve. This will give us back a result that we can go ahead and put on a map. So here we are, we have Berlin, Germany, and we're going to add this information on. And we have our stop locations shown on here. So the start and stop of our routes. Seeing it visually is great, but oftentimes you want to read the directions to get from point A to point B. We can get that as well. In the attributes that are returned for each of the point locations, there are directions. And we can easily load this into a pandas data frame and display it. So we have our starting location where we started, and then we go through from our starting location to our ending location, and we see all our information displayed, and it gives us the length and the time of how long we're going to be on that road. Now let's take a little bit of a deeper dive and seeing another application of using network analysts along with other tools to get an insight. And we're going to talk about walking to school or having safe streets to schools. And unfortunately, every day, incidents like this become more and more frequent, where you see 2 die, 8 hurt in Pasadena as vehicle hits a crowd. And the question is how can we use the power of the Python API to help us prevent these incidents from ever happening again? To do this, we have to uncover patterns and look at data, and then to do our analysis. And we're going to follow the general workflow. We're going to look at the points as a whole and calculate densities, and we're going to find hotspots, and then we're also going to render it using a heat map renderer. We're then going to take these collisions and we're going to filter it down and look at it differently using symbology and arcade expressions. Finally, we're going to take our school layers in Pasadena, create some drive time areas, and summarize within and find the top 5 most dangerous schools. But first we have to set up our environment like we did before. So we're going to perform our imports, and we're going to go ahead after that import, and we're going to go ahead and connect to our GIS. Once we have that, we're going to pull in our traffic collisions from ArcGIS Online. We can go ahead and we can interrogate the layer to see how many layers we have, and we can see that all information for the traffic collisions since 2008 exists on one feature layer. So let's pull this information in. Let's access the individual layer and plot it on a map. When we look at this map, we really can't discern any meaningful patterns. So let's dig a little deeper. I'm going to pull the information in as a spatial-enabled data frame, and I'm going to see the unique values that exist within the type of collisions that have occurred. We're interested in 2 types because we're talking about children, and that's pedestrian and bicycles. But we can see that all these collisions, we can see that there are a whole host of other collisions that we need to filter out. So let's go back to our layer, apply a filter, and say that if it's a bicycle or pedestrian, we want to return those types. The other ones we can ignore. Now that we've set up our layer to have that filter, we can start gaining insight. First, we're going to do it visually. And to do this, we're going to calculate density. So we're going to take our filtered feature layer, pass it in, and calculate the density and hotspot. I'm going to take advantage of the future syntax and have these fire off at the same time. We see we get back 2 separate result objects. I'm then going to go ahead and collect the results and get the layers that I need. First, let's look at the density. And we can see that we do have high concentrations within Pasadena, especially at the areas in purple right here. Looking at the hotspots, we can back it up statistically, showing that we have some statistically significant clusters in the area. And then just for a sharper visualization, we can use heat map rendering to show this data. But it's still hard to understand the data, so let's symbolize it by category. We're going to use the spatial-enabled data frame, filter out the types that we need, so we have the pedestrians or bicycles, and we get a look of the top 5 results. Now we're going to go ahead and we're going to do accidents involving pedestrians and fatalities, pedestrians and injuries, cyclists and fatalities, and cyclists and injuries. So that's how we're going to symbolize our data. To do that, we're going to use Arcade, and Arcade makes it very simple. We specify the our field, the fatalities, injured, and the various types of queries that we want. We can then go ahead and use the create symbol function and pass in those arcade values for each one. Once we have that, we can display it on a map. And now we can see where the predominant type of injury is occurring, where the large circle is pedestrian fatality and the large blue is bicycle fatality. And then we have pedestrian injuries and bike injuries. And you can see the distribution better than just having one continuous surface. Now we're ready to explore the areas of the schools to find the top 5 most dangerous school areas in the Pasadena Unified School District. So we're going to pull in this information doing a simple gis.content.search and get back our school's item. We're going to go ahead and plot that on the map with a map that we had before, where we had the rendered, and we can see where the schools are. And we can kind of see that there's areas where we do have high concentrations of schools, but it's still hard to tell which is the most dangerous. So to do this, we're going to use something that we saw before in our session, and that's using the create drive time analysis. We're going to pull in that school layer, and we're going to do a class break on 0.5 miles, because that's the average walking time for students to walk to school in a lot of districts across the United States. So we're sort of generalizing. And we're going to save it out to a hosted feature service layer called PSUD schools drive time. The system will create that. Once we have that, we can summarize the total number of collisions within those polygons. And then we can get the top 5 most dangerous. So we take our dangerous areas and the layer, we're going to query it as a DF, sort the values by the point count, and then look at the top 5 results, and we get that on the map. We can then plot those areas, the school areas on the map, save it out, and provide it to the administrators who have to make the decisions to keep our kids safe and secure when they go to and from school. So what we saw is that we can use geocoding along with a whole bunch of other tools, geocoding, network analysis, and analysis combined together, and get really strong results back that can help you gain insights to what's going on for the incident, for the thing you're trying to figure out. The next component that I want to talk about is geo-enrichment, and this is going to allow us to take our data and provide additional demographic or business data. So we saw on the analysis side, we saw the enrich function, but we also have a specific model that's there to deal with geo-enrichment called ArcGIS.geoenrichment. And this will give us very detailed information, and you can really control a lot of the different things you add to your data. And this includes where you can enrich points, lines, and polygon geometries, service areas, addresses, and it gives you the ability to create custom reports and also charts. And these are fully customizable for these functions. So we can say we need to create a report about Redlands. We want to get the tapestry profile for the area. We can export it out to a PDF or a CSV file. And then we can even theme it to match our company. So now I'm going to hand it over to Atma, who's going to talk about imagery and raster analysis. All right, Atma, take it away.
Thank you, Andrew. That was fantastic. Now, for the next part of our talk, we're going to talk about how you can perform analysis against your imagery and raster data using the Python API. Primarily, we're going to be looking at tools that are exposed out of ArcGIS.raster module. Just like how you can search vector data, you can search for imagery or raster data using gis.content.search, and you get back items. And then you can look at the layers within the item, which give you imagery layer objects. You can add them to a live and interactive map. You can visualize, zoom and pan and look around. But oftentimes you will notice that imagery data contains not just 3 bands, R, G, and B, but they come with many more bands. So you can use the API to pick the bands that you choose and make a band combination, and render that on the map widget. Sometimes these imagery layers might come with something called as raster functions. In this case, this is a Landsat layer and it comes with a few different raster functions. These functions can do scientific analysis, or they can also enhance the visualization of your data set. In this case, these are a bunch of raster functions that choose different sets of band combinations and apply different kinds of structures on them for different applications. Like for instance, agriculture, bathymetry, or vegetation index, or band combinations for looking at atmospheric opacity and things like that. In addition to raster functions that are already published with your imagery layer, Python API comes with over 140 raster functions, and you can do an assortment of things. Like you can use them for performing mathematical operations on your raster or cells in your imagery. You can do conditionals, you can do data management, like converting from raster to vector, vector to raster, etc. You can perform interpolations, you can perform density analysis, overlay analysis, zonal operations, etc. The important aspect of the raster function is that it allows you to chain them with one to another. So you can take the output of one raster function, feed it as an input to another raster function. Like this, you can build a workflow like as shown in the slide deck over here. So for instance, if you want to do a suitability analysis using raster module, how would you do that? For example, let's consider building a suitability model to find good places to go running in San Diego. Some conditions are it should be farther away from human impact. So it should be a natural landscape, not a built-up area. It should not be very steep. It should not be very hilly. And you have different percentages indicating how important these different criteria is. This is a very standard suitability model that you would build. And let's see how you can use Python API to do that against your WebGIS. First, you go and collect the input data sets. You collect the elevation data, then you collect a human modification index layer, which is a modified land use layer. Then you clip it to your area of extent. Here in this case, we're clipping it to San Diego using the clip raster function. Then you're composing the different layers. Like for instance, you're applying a remap on the elevation layer. Remap is a function that if you give it a set of input values and a set of ranges and what those output values should look like, it'll change the input values to match the range that you provided and give you an output. Like that, we are applying remap on elevation, then we are using a slope function on the elevation layer and applying a remap to get a terrain layer. And similarly, we're doing that for the natural areas to find areas that are farther away from built-up land. Then you can apply this raster calculator as shown in the cell on the top. Imagine these as weights or importance of different criteria, and just like that, you can just multiply these weights along with these layers and you can produce a result. Then you clip it to your area of extent and you apply a color map, and ta-da! You have your suitability model visualized with varying ranges of red to green, showing how suitable or unsuitable the places are for going running in San Diego. Now, all of this is temporary and nothing is persisted. It's what we call this on-the-fly analysis. So it is only performed for the region of extent that you query for. It's very lightweight and very fast because it's performing these as on-the-fly analysis and only at the display resolution. If you want to persist this result and create an imagery layer that you can, share it with others or use it in some other downstream analysis, you can simply call save. The importance behind the scenes, what happens is the processing chain that you applied is applied on the different input rasters that you have provided, and the computation happens at the imagery's source resolution, and a new imagery layer is produced as a result. Now, let's take a look at a demo that performs suitability analysis using raster analysis. My objective here is I want to find suitable areas for placing these automated external defibrillator devices. You would have seen devices like this if you have come to the user conference in San Diego. You find a lot of these placed on the walls. And the city of Pittsburgh had the same kind of a problem that they were trying to solve. They were trying to identify suitable places to locate these automated AED devices in public. And they had specific criteria that they already knew indicating what places are suitable and what places are not. So this notebook is going to walk us through the process of building that suitability model using the Python API. So we started off by querying what the kind of input data that we have. In this case, there is a feature layer, and it has a bunch of other layers inside it. We have the heart attack incidence dataset, which is a point data that indicates how many cardiac arrests have happened outside of hospital. And then we have streets, and then we have zoning, and then and boundary layer for the city of Pittsburgh. You can load it on a map widget, and you can visualize this. So all the blue dots indicate heart attacks, and the size of the dots indicate the number of incidences of heart attack in that particular location. And then we have the zoning map, where gray color indicates residential area, and red color indicates commercial, and everything else is non-commercial is indicated as light green. So the suitability model looks like this. Where would you place these AED devices? These have to be placed in locations where people can access them. So it has to be commercial, and it has to be easily accessible. And also you place devices where there is a history of out-of-hospital, high incidence of out-of-hospital cardiac arrest. So the density of the number of attacks, heart attacks, is also important. And you perform an overlay analysis combining these two criteria, and you filter out the results. So let's start by building a 600-foot buffer around the commercial area. So the idea is these areas are commercial, so they are easily accessible to public, and there are good amount of people given any time of the day to make use of these AED devices. To start off, we are going to query our feature layer. Our feature layer may contain a large number of results, a large number of records. So if you build a query that's going to query all of this, then it might take a large amount of time, long amount of time. So one way to get around this is to build a query and only get the first 5 records. And that's what I'm doing here. I'm looking at the results as a data frame. The idea is to just understand what kind of content is already present in this layer. So by looking at this data frame, I know there are columns like perimeter, there are columns that contain a code, a name of that particular area. And the important thing here is that it has the zoning information, whether it is residential, commercial, non-commercial, etc. Now that I know what the data contains, I can actually construct the proper query. So in this case, I'm only interested in polygons that are commercial in nature. So I'm constructing my where class, zoning group equals commercial. Then I'm getting the results back and looking at it as a data frame. I'm only displaying the top 5 records. So don't think that there are only 5 polygons. I'm only looking at the top 5 or the first 5 of those polygons. When I call the shape, I know that there are 317 polygons that matches criteria. Now I can create a map. I can go ahead and draw that on this map, and you see these are the different polygons that are commercial in nature. Now that we have these polygons, we can apply a buffer of 600 feet around it, so we can proceed with our analysis. So normally what we would do is, now that you have this feature set that contains the query results, you will send this back to the server and ask the server to run buffer on it. That paradigm will work because this data set is not very large, and it'll take quite a short amount of time to compute it. But what if your query results in a really large amount of data? It is not very efficient to send data back and forth between client and server like this. The ideal way to do that would be to ask the server to go get the data set right from the feature layer that you originally started with, and then apply these queries on that and only get the results that are matching your criteria. That's what we're doing here. So on the feature layer object, we are using the filter property, and we are feeding in the same exact clause that you gave in the where clause when you ran the query earlier, saying that the zoning grouped column should be commercial. If you're familiar with ArcGIS Pro or ArcMap, you would have come across a terminology called definition queries. That is what we are doing it here. We are applying a definition query on this feature layer. Then, when I call the create buffers tool on the server, I can give this particular feature layer, and the server will know, or Python API will tell the server to make use of this particular definition query or the filter and apply the buffer only on those polygons that match this criteria. As a result, we get back an output, and now we can put it back on the map, and you see that these buffers are only applied on the polygons that match the criteria, which is commercial districts. Next, we're going on to the other dataset that we have, which is out-of-hospital cardiac arrest. We are running a query. Similarly, we're just getting the top 10 records in this case, and we're looking at it as a data frame. So we know what kind of columns are there, what kind of data is there, what the data type is, etc. What we want to do next is somehow quantify the number of incidents, the number of attacks that happen in a particular place. One way to do that is to do density analysis. So we make use of a tool called calculate density, and we use that against the raster module. So as a result, this is the raster data that is created by analyzing the different points that represent the number of cardiac arrests. This itself is not very meaningful beyond the fact that saying that the pixels that are bright in color have large number of incidences of heart attacks, and the pixels that are gray or black do not have or have fewer number of incidents. Now, the rest of the analysis goes into how do you interpret this and how do you make use of this in building the suitability model. So what we do next is we're trying to look at the histogram of that particular raster data. So we are calling, hey, density layer, give me your histograms, and then we are using matplotlib to construct a histogram chart. So let's look at the chart on the outside, which contains the number of pixels, and the x-axis shows you the number of heart attacks per square mile. The one over here is a zoom up of this particular range as shown here. As you can see, pixels that have fewer heart attacks are more, whereas pixels that have larger number of heart attacks are fewer. The idea here is that we are only interested in these kind of pixels. These are the regions that show that have large amount of heart attacks, and we need to somehow extract that information from the density layer and use it for our analysis. So how do we do that? First, we want to convert the units for this density raster. The raster gives you the number of pixels, number of points, in a particular square mile. But the heuristic given to us for placing these heart attack AED devices is that we need to calculate in 5-block radius. So we know that we know the area that is covered by a 5-block 5 by 5 square blocks, and we're trying to convert and do a unit conversion on the density raster so that we can get the results back in terms of square blocks. And that's what this raster is. It doesn't look different from the original because we're just converting the units. Next, we are applying a color map so we can see the variations a little bit more easily. Now, finally, what we want to do is do the remap. This is the same function as we saw on the slide deck. What we want to do is we are only interested in locations or pixels that have at least greater than 5 heart attacks within a 5 by 5 city block. Everything else will become no data. And remap is extremely helpful to do that kind of conversion. And we apply a color map on that, and we are visualizing that. So we know that there are 3 regions that have high density of at least more than 5 heart attacks within a 5 by 5 block radius. We can throw it on a map and we can visualize what these areas are. Now we need to combine this high incidence of heart attacks with access to public, which is commercial areas, and we can do that simply by doing a bitwise AND. But before we go into that step, we need to, one thing that we didn't realize is the buffers that you obtained earlier was a feature data set, whereas the density is a raster data set. So we need to convert either one of them to a raster or the other one to a feature data set. So in this case, we are converting feature to raster. So we're turning that buffered polygons into a raster data set. Next, we can do a bitwise AND, and we can find of all those places that have high incidence, which are those places that are more accessible to the public. So we narrow down to 3 different areas. We can throw it on a map. We know what these areas are now. And so we can give it to the city officials so they can narrow down further and figure out which places are suitable for placing AED devices. So this was one quick example of showing how you can perform suitability analysis on raster dataset using the Python API. Now let's jump back to the slides. So far in this talk, we have seen how we can perform various kinds of spatial GIS analysis using the Python API. A lot of times we use tools that are built within the ArcGIS ecosystem. But as users of Python, you would know that the scientific Python ecosystem is really vast. There are so many different libraries for performing various kinds of analysis that are outside of ArcGIS. The good news is the Python API allows you to make use of those libraries and combine them with the tools that are provided within ArcGIS, so you can build a comprehensive set of analysis. Things like you can do data wrangling using pandas and NumPy. The spatially enabled data frame that we saw in the talk makes use of pandas data frames. And then you can make use of machine learning libraries like scikit-learn, TensorFlow, PyTorch, FastAI, and you can use open source library like GeoPandas, GDAL, PySal. You can also use image processing libraries, etc. There's only a sampling of a few of them over here, but you can make use of many more than what is actually shown here. So for the next part, I'm going to show you a quick demo of how you can combine the analysis tools in ArcGIS and the scientific Python ecosystem to build a machine learning model. So let's get started. I have a data set that is provided by the USDA Forest Service, and it contains historical GIS data set of forest fires from 1992 to 2015. It has a lot of ancillary information, and I want to build a model that will predict a cost given a fire, given a time, given a place. I want to predict what would have been a cost for that particular fire. So this notebook walks us through that particular building a model that will answer that question. So we go ahead and we can download this zip file. This zip file is shared over here that contains the geodatabase as a zip file, and we use Python to download that. Then we can extract it, look at the contents. Then we can use spatial.from feature class and pass the path to the particular geodatabase and the feature class within the geodatabase. And now we have a spatially enabled data frame. It's a really large data frame. There are over 1.8 million points or polygons within this, indicating fires for the last 20 or so years. We can look at the columns and filter out only those columns that are more relevant to us in this study. So that's what we are looking at here. So we know that there's a fire year, there's a fire date, which is a datetime object, and then there's a cause saying that what was the reason that caused the fire, and so on. We can use matplotlib or the built-in plotting within pandas to quickly build a bar plot that shows what were the different causes that led to the fire. So from this we can see that burning debris happens to be the most common cause for starting a fire, followed by arson and lightning and so on. Next, what we can do is, because this is a GIS data set and there is also a state column, we can ask pandas to tell me which states have the most amount of fires. And it happens to be California, followed by Georgia, Texas, North Carolina, and so on. We can do quickly these kind of exploratory analysis using pandas and matplotlib. What we want to do next is, like I said earlier, we want to identify the causes, or we want to build a model that can understand what causes led to a particular fire. And to do that, we need to deconstruct this data set that we have and build many more descriptive columns. For instance, we know that there is a discovery date column over here, and it is a datetime object. Now we need to split this up into year, month, time, and time of the day, time or day of the week, and so on. And that's what this cell does. It tries to split them up. And then, now that you have it all split up, you can ask again pandas to create a plot that shows how the variations of number of fires happened over the years. And then we can fit a trend line to understand if there is an increasing trend or a decreasing trend when it comes to the number of fires over the years. Does the day of the week matter? We can also put it on a plot to understand. For arson and lightning, it turns out to be for arson, Sunday happens to be the day that had most fires have started due to arson. Then we are trying to use scikit-learn library to build a machine learning model to understand what causes led to a fire. But the number of columns that we have so far is not sufficient to build a predictive model. So this is where geo-enrichment comes into play. So we can use the geo-enrichment module of the Python API and pick up some variables that are more informative or more related to forest fires, like the population density, diversity index, male, female, gender, population, age, income criteria, education levels, and so on. This is arbitrary, but you are allowed to use as many more variables as you see fit in creating this enhanced data set or data engineered data set. Then we call the enrich method and pass these variables, and we also pass the input data frame that we need. And as a result, we have the same input data frame that has our location columns. In addition to that, we also have all these additional variables that are being queried from your geo-enrichment service and added into our data set. Now that we have a highly engineered and a really large data set, we can go ahead and perform machine learning on that. So in this case, we are trying to fit a random forest classifier. We are splitting our data set into training and test sets. And we're calling fit, and we're trying to do we are trying to look at the accuracy of our model, and it turns out to be 92% accurate. This is a very quick demo of how you can take data set from ArcGIS, a file database, then you engineered that using geo-enrichment service. Then you used the random forest classifier from scikit-learn library to quickly build a machine learning model, a tool that's probably not available within ArcGIS. Whereas the forest-based classification is now available in the recent versions, but you can use other tools, other models that are in scikit-learn but not in ArcGIS to build a machine learning model to predict the causes for forest fire in this case. One example of how you would use this is something that we didn't show here is a lot of our records do not have this information. They do not have what was the cause that led to the forest fire, this particular column. So they have missing data in this. So the idea is, if you have missing data like this, can you build a model that will learn from existing data and using the features that are existing in the dataset, as well as using additional geoengineered data features. And then can those model go and fill those missing values in a more intelligent manner? And what would be the accuracy of that particular operation? So that's an example, that's a possible use case for this case study. Now let's go back to our slides. Let's do a recap. Throughout the study, we have seen how you can perform GIS analysis and data science with ArcGIS API for Python. The very first problem people encounter when you're doing data science is access to data. So if you do not have data, you cannot really perform any kind of analysis. This is where you can use a Python API to easily query the data sets that are within your organization. You can, once all of your users have named user accounts on your portal or ArcGIS Online, and you start publishing the datasets on your WebGIS, you can easily search for each other's content. In addition to that, you can also make use of the curated content from Esri as part of the living atlas. So for instance, the Landsat layer that we discussed earlier and the elevation layer that we saw in the slide deck earlier for the raster analysis were all layers from the living atlas. You have a multitude of layer datasets, imagery datasets that are multispectral, high spatial resolution as well, base map layers, transportation layers, boundaries, and so on. Then, when you start connecting to your ArcGIS Online, you can also search for datasets that other analysts and scientists like you are sharing on ArcGIS Online. This is a really excellent source of dataset. And also a lot of civic bodies and governments, as part of their open data initiatives, are starting to share authoritative information on ArcGIS open data portals. So all of this is just one search away for you to start building your data science models. Visualization is a key part, and often it is an iterative part when you're doing a data science. So we saw using Jupyter Notebook and the map widget, how you can quickly visualize your maps using smart mapping, using raster functions, and using various other renderers. In addition to that, you can also make use of third-party visualization libraries, like for instance, built-in plotting library within pandas. Libraries like Data Shader, Plotly, or Seaborn can also be used along with your Python API in Jupyter notebooks to visualize your datasets. This whole talk was about analysis. We saw how you can perform analysis using tools within ArcGIS, like performing spatial analysis, network, geocoding, geo-enrichment, how you can analyze raster data, and also how you can use ArcPy to perform your analysis. In addition to that, towards the end, we also saw how you can make use of the analysis tools available within the scientific Python ecosystem. So you can mix and match tools within ArcGIS and tools outside of ArcGIS and produce a comprehensive study. The last part, and probably one of the most important parts of performing analysis and being a data scientist, is how you disseminate the analytical outputs to stakeholders or citizens. Some examples are you can produce web maps and web scenes. For instance, you're building a predictive model that identifies places that or that identifies or kind of predicts where accidents would happen. One way to do that is to publish these results periodically as web layers and push it on your WebGIS. These are very accessible, and it's a very good way of democratizing your data science and deploying that to the end users. Jupyter notebooks by themselves are a good source to produce a rich narrative study. A lot of these samples in the notebooks that you saw today have a lot of text, they have a lot of images, you can also embed videos, and you can also embed maps and iframe any kind of dashboard into your notebook. And then you can share the notebook to anyone else. They have this rich narrative that you produced, they can understand the context for doing an analysis, a lot of text around it, and also have a live code so they can rerun the analysis or change and tweak your parameters and build another analytical output. So this kind of really encourages the reproducible research concept that we see going around in the academic circles. Another option is to deploy them as dashboards. Bottom right over here, you see a change detection dashboard that is built using Jupyter dashboard plugin. You can use that, or you can build operations dashboard with ArcGIS, or you can also use third-party modules like Plotly to build dashboards. So that concludes our talk today about how to use Python API for performing GIS analysis and data science. Thanks, everyone.